I want to thank everybody for coming this evening. This evening our speaker is Donald Anthony, who's with Great Point Energy. He's one of their technology leaders, and he has a bachelor's degree in chemical engineering from the University of Toledo and a doctor's degree from MIT, working in the gasification area for his PhD work, and he's worked in other areas, and now he's back working in that area again. And I think it's becoming more important in terms of its commercial potential, and we're very thankful that you've chosen to come and be with us tonight, and thank you for the presentation that you're going to make. So we welcome you, and you can put that on your tie, probably. The other one in the pocket or on your belt. Yeah, we will do that.
Well, thank you, Larry. Good evening. All grad students? Some undergrads here. Great. One of the morals that will come out of this talk is the importance of doing a good thesis. 2003, I am president and executive director of the Council for Chemical Research, sitting in my office in Washington, D.C. I got a phone call. A young fellow from Cambridge, Massachusetts said, "Dr. Anthony, I've just been reading your 1974 PhD thesis." And I kind of sort of chuckled. I thought he was joking or pulling my leg, and honest to God, he might have been the only person that actually read that entire document. But he said, "We're really interested in developing a new coal gasification technology, and we'd like you to come up to Cambridge and consult with us." And I said, "No." And he said, "Oh, well, could we come to Washington, D.C.?" And he said, "Well, sure." And so they came down. 3 of them showed up, and I promptly told them, "Fellas, this is kind of a clever idea, but you've got no chance. There is no way you will succeed in doing this. You have no idea what it would cost to develop this technology." And they said, "Well, yeah, we understand, but we're going to try." And 2 months later, they called me up and said, "We've got 2 venture capitalists that are ready to invest in our company. Would you talk to them?" And I said, "But you know what I'm going to tell them? I'm going to tell them it's a bad investment." And he said, "That's okay. They want to talk to you." So I told the 2 venture capitalists it's a bad investment. They both smiled and said, "Yeah, but we kind of like the idea." So they put their money in. A year later, these young guys got 2 more venture capitalists. In fact, the 2 largest venture capitalists in the world, Kleiner Perkins and Vinod Khosla, to back this thing. And then a year later, they talked the Dow Chemical Company. And at that time, what was a pretty impressive financial organization, in today's news, not so impressive, but Citibank said they were in it. And at that point, I finally said, well, maybe they can pull this thing off. And so I agreed to join the company. But what I'm going to tell you a little bit about tonight is what we have labeled catalytic hydromethanation. We kind of coined that term because the term gasification, when we were talking to non-technical folks in Washington, D.C. and the state houses, sort of immediately assumed what we were doing, and then it became very difficult to explain why it wasn't the same as every other gasification project they had heard about. So we call it catalytic methanation. And very simply, we take coal, petroleum coke, biomass, and convert it to methane, which is essentially pipeline natural gas. In this case, since we're manufacturing it, we call it synthetic natural gas to distinguish it from the gas people find in the ground. Let me kind of go through this thing a little bit here. Let's see what's the easiest way to do this now. There we go. But let me tell you a little bit about the company to give you a little flavor for who we are and what we do. Then I'll talk a little bit about the technology, and then for the benefit of the chemical engineers among you, we'll talk about what we're really focused on from an engineering standpoint, which is scale up of the reactor and the approach we're taking. And then maybe something I don't know whether you get in the university community, but how do you manage the risks of a scale up in a commercial world? And I'll take you a little bit through what we did there. And I'm informal. If you got questions during the talk, interrupt. Let's get them answered. No problem. Okay, corporate overview. Business concept. Already told you we're taking this hydromethanation technology. We want to manufacture pipeline quality synthetic natural gas from coal, petroleum, coke, biomass. Reasons are threefold. Number one, and relevant to the subject of this seminar, sustainability or environmental cleanliness. Of all the commercial hydrocarbon fuels, I think it's generally agreed methane or natural gas is the cleanest. Our approach makes it an environmentally friendly alternative to what most coal ends up being used today. 95% of the coal mined in this country is burned to produce power. We think we've got an environmentally friendly alternative to that. We've got virtually zero CO2 emissions from the process, basically because we capture the CO2 that is produced and ultimately can sequester it. The process basically, again, from an economic sustainability perspective, enables a low-cost and abundant source of new natural gas. We feel, as I'll show you a little later, manufacturing methane this way is actually cheaper than drilling for it these days or importing natural gas. We've got virtually unlimited domestic and global supplies of coal and petroleum coke, and we see enormous value arbitrage between them. And the company is rather uniquely positioned. We intend to move forward and build, own, and operate the facilities for the manufacture of gas. It's pretty distinctive, and the reason we mention that is because most, in fact all of the gasification technologies were developed by companies that then licensed them, did not actually use them themselves. And so it made it quite difficult to get the technology into the marketplace. Perhaps with the exception of Citi's current reputation, we have a fairly stellar group of investors, and we are looking at licensing the technology in a global fashion. As I said before, the company was founded in 2003 by three highly successful entrepreneurs. All three of these gentlemen are in their early 30s. Between them, they've started and sold off 6 different companies. They sold a chip manufacturing technology to AMD. They sold a voice over internet protocol company to Deutsche Telekom. They developed a biopharmaceutical company. They've done a number of very interesting things. In 2000, they decided that high tech wasn't where they wanted to be. Energy looked like the new opportunity. So they started, as most entrepreneurs from the high-tech community, they started working on fuel cells. They got the idea, well, could you drive a fuel cell with coal? And, well, if you gasify the coal and put the gas in the fuel cell, and pretty soon they began looking at the gasification of coal and said, well, maybe there's something here. And they got interested in the gasification of coal, came across some research that was being done at Southern Illinois University, of all places, on catalytic gasification of coal. Hired the professor, hired his student, hired the students working in the adjacent labs, and basically began to do some work on this technology. The first 2 venture capitalists that backed them were Draper Fisher Jurvetson and Advanced Technology Ventures, and then Kleiner Perkins and Khosla came on board, and then Citi and Dow led the last round, and that round included Peabody Coal, AES, which is one of the large privatized power developers, and Suncor Energy. Suncor is a spinoff of the Sun Oil Company. It's the company that produces bitumen from the Alaskan or the Albertan oil sands. So they are the largest oil sands production company in the world. Dow is probably the largest consumer industrially of natural gas in this country. Suncor is the largest consumer of natural gas in Canada, and right now Suncor is on a trajectory that they will become the largest consumer of natural gas in the world by 2015. Company's built a very strong intellectual property position in the technology. We've confirmed it at lab and pilot scale. We've put together a very strong team and got a staff of about 100 folks right now. The market is really natural gas. very large market, growing fairly rapidly, and we suspect it will grow even more rapidly if carbon constraints come into play. In other words, it's the least carbon emitting of the hydrocarbon fuels. Right now, we've got about 10 years of supply at current consumption rates. Demand continues to grow, and we're simply not replacing the gas as rapidly. Prices increased very rapidly. You can kind of see the pattern here of what happened to natural gas prices over the last few years. They've fallen very recently, but are still up in the $6 range in the spot market, and more like $8 to $9 in the futures market when people begin to project out a few years. Right now, U.S. demand for natural gas is expected by most analysts that it will have to be met with imported LNG, and that's currently trading basically at parity with crude oil around the world. At the same time, we've got the largest coal reserves in the world, roughly 250 years of supply at current consumption, as contrasted with 10 years of supply of natural gas. There are also very large coal resources in China, India, and Russia. One of the things the company didn't anticipate initially was the importance of petroleum coke, but petroleum coke is one of the major waste products that's currently just being landfilled in Alberta as they basically upgrade the heavy oil. They coke the oil, leave the carbon behind, and get kind of a syncrude from it. And so there are enormous stockpiles of petroleum coke and growing every day. And as the crude oil slates around the world get heavier and heavier, more refineries are putting in coking capacity and creating an additional supply of petroleum coke. And as you can see here, the price of coal and petroleum coke have remained very, very low relative to oil and natural gas. Little background. Converting coal to gas is not new. We were doing it in the States in the 19th century. Used to make a low BTU town gas that was used to heat street lamps or light street lamps, various applications. That sort of disappeared with the discovery of oil in the country and ultimately natural gas. But in World War II, the Germans resurrected coal gasification technology as a first step to making liquid fuels when they were cut off from global oil supplies. In the days of apartheid, South Africa was forced to look to its own resources to supply its energy needs, and they began gasifying coal and then catalytically converting these to liquids. And it's been used for nearly 50 years to convert coal into synthesis gas for chemicals. One good example is Eastman Chemicals in Tennessee. Has been using coal gasification since the mid-'80s for chemicals production. First gasification power plant in the States was 1984 at the Coolwater site in California. And the folks that kind of keep track of this say there's something approaching 400 gasifiers throughout the world in commercial use. So with all that, what are we doing new? Well, one thing that Great Point Energy does that's not done in a single one of these 385 gasifiers is to put a catalyst in the gasifier. Essentially, we mix the coal or petroleum coke with steam and the presence of the catalyst, and that reacts to form methane. Now, we've known how to make methane from coal for a very long time. In fact, there's a very large facility up in North Dakota that commercially manufactures synthetic natural gas from coal. It was built in the early 80s, went bankrupt, never made any money until a few years ago when the price of natural gas finally rose to a certain point. What they do and what people have known how to do for a long time is really kind of shown in these reactions. You can gasify carbon with steam to make carbon monoxide and hydrogen synthesis gas. You can shift the synthesis gas, basically push that reaction to the right by adding water or steam to make a hydrogen-rich synthesis gas. And the idea is to shift it so you've got about 3 hydrogens to every carbon monoxide. And then catalytically you can react that to methane and get back 1 molecule of steam. If you add those three reactions together, just add them together, you get the overall reaction. 2 carbons plus 2 waters make methane plus CO2. And that's the essence of synthetic natural gas. The problem is when you do the reactions separately, as the technology exists today, is the gasification reaction is highly endothermic and is favored at high temperatures. So basically you've got to run a very high temperature gasification reaction that consumes a great deal of heat at high temperatures. The shift reaction's thermally neutral, but all the heat comes back in the methanation reaction. Unfortunately, it's a low temperature reaction. So you get your energy back at this point. When you add the 3 reactions, the overall reaction's essentially thermally neutral. Doesn't require, it's neither endothermic nor exothermic. The problem you have when you separate the reactions is you're producing heat at low temperature and you've got to pump it uphill to drive a high temperature reaction. The advantage of the catalyst that Great Point Energy adds is that it allows this reaction to occur in a single reactor. So we actually run our reactor, a fluidized bed reactor, at much lower temperatures than most gasifiers, aided by the presence of the catalyst, and essentially we make methane and carbon dioxide, the only products we make in net out of the reactor. To put that all together in a process looks something like the following. And I have this highlighted in light blue. This is essentially the proprietary technology that Great Point Energy has. We bring in a ground coal, we add catalyst, feed it to the fluidized bed. The fluidized bed is fluidized with a mixture of steam and synthesis gas, and we make our product gas here. We take out the unreacted char, mineral matter in the coal, and our catalyst. We recover our catalyst, little makeup here, and recycle it. That's the proprietary technology. The gas that comes off is, rough terms, it's a quarter steam, excess steam in the reaction, a quarter methane, a quarter CO2, and a quarter synthesis gas. We bring that down, we cool it, we scrub off the trace ammonia from the nitrogen in the coal. We then use an acid gas removal step to take away both the CO2 and the hydrogen sulfide, recover CO2 and sulfur. And then we've got a little trim methanation. That little bit of synthesis gas in there is catalytically converted to methane, so we essentially end up with a pure methane product. This syngas over here is actually balanced by the syngas here so that there's no net production of syngas in the system, and so that our overall economics are driven by methane. We generate the steam using a partial oxidation system to generate both steam and synthesis gas and the front end handling. The commercial plant, this light blue area, our proprietary technology, represents about 15% of the capital investment of the plant. 50% of the plant is just in the cleanup and final processing of the gas, and then you've got the other 35% in both the front end coal handling and grinding and the steam generation, all conventional technologies. The advantage of doing this relative to a conventional synthetic gas manufacturer is that we have a much higher thermal efficiency. In other words, for every BTU of coal or petroleum coke you bring into the plant, we get 75 or to 80% of those BTUs back in final product methane for sale. The technology that's now being operated up in Great Plains, North Dakota, is closer to 50%, and some of the best designs I've seen might squeeze up into the low 60s. Almost impossible to do any better than that. So we've got 20 to 50% higher thermal efficiency. And because the plant's much simpler, we've got about 30 to 50% lower capital intensity. In other words, the number of dollars you've got to invest to get an amount of methane out of the plant. And these two advantages kind of manifest themselves in a much lower cost of gas. We did two scenarios here, one using Powder River Basin coal in Wyoming, the other one using Alberta petroleum coke. We're looking at cost of gas, including the return of capital, somewhere between $4.50 and $5.50 a million BTUs, or a standard cubic foot. or 1,000 cubic foot. Prices on the NYMEX for futures in natural gas, and we typically look out 2 to 4 years, are somewhere in the mid $8 to $9 a range. The best conventional technology is probably capable of manufacturing gas in that same price range. If the gas is essentially free internationally, you could liquefy it and ship it for $7 to $8 to the country, but right now Chinese and Japanese are paying something more like $12 or $13. That's simply the competitive price for LNG. And drilling for oil, new natural gas supplies, and people are doing a lot of drilling into the Devonian shales and a number of other areas, and most indications are we're probably looking at $6.50, $7, maybe approaching $8 per million BTUs. So we've got a fairly significant economic advantage as we look at those alternatives. We've built up a very strong intellectual property portfolio. We've filed in the last 5 years something like 42 patents. We have global coverage. We're looking now at licensing, but basically we've got patents that cover the process, byproduct use, the nature of the catalyst, how you apply it, and even some clever ideas on processing the gas. So the question is, how do you scale this thing up from small scale to large scale? The initial experiments were done in the laboratory, and these are little 2-inch heated tubes, and basically showed the effect of the catalyst. Here's the gasification of the coal, or I guess in this case I think we're doing petroleum coke, no catalyst. And after 6 hours, 5-6 hours, you're probably 20-30% gasified. Same amount of time with the catalyst present, you can get up to 95+% conversion of the coal. So this is what happened in the laboratory. And this work was completed in 2005, 2006. In 2006, we decided to look for a pilot plant to scale this thing up. We considered the possibility of building one. It looked like it would take too long, cost too much money. So we found that the Gas Technology Institute had a fluidized bed pilot plant for coal gasification. So we leased it and then modified it to run the Great Point Energy reaction. That testing was done in 2007, and now in 2008, the team is actually designing for the next scale-up step. That next plant will be built over the 2009-2012 time frame, and then you will be basically, hopefully, into commercial operation in the 2012 and beyond period. The leased facility basically operated very well. We had close to 1,200 hours of online operation, 17 stable, steady state periods. We managed startup, shutdown. The reactor performed basically as predicted. We were able to test both Powder River Basin coal, petroleum coke. We were able to add, remove, and recover the catalyst successfully. And we had people looking over the shoulders of the team every step of the way. Dow Chemical, for example, sent a couple engineers down for every pilot plant run. They took the raw data, went back to Midland, did their own calculations, and then we compared those with them. So a very thorough process. The trick was, how do you go from a pilot plant to a larger unit? And what we decided to do is to go use a very sophisticated mathematical model to incorporate the chemistry, reaction kinetics of what's occurring in the system, and the hydrodynamics of a two-phase bubbling fluidized bed. The math model was built, and then essentially we took the pilot data and used it to validate the model. In other words, basically confirm the model over a very wide range of operating conditions. We also ran cold flow experiments to give us some additional information on different types of bubbling beds. And then the fellows even went a little bit further and used some computational fluid dynamics to give them a more sophisticated look at the characteristics of the fluidized bed. What we were able to do in the pilot plant was to confirm the kinetics and the thermodynamics. The problem was that when you get to a small scale pilot plant, fluidized bed, the wall effects become very, very significant in terms of affecting the hydrodynamics. Essentially, as those bubbles form off the grid, they'll bridge across a fairly good sized dimension. We had up to 12 to 18 inches in the pilot plant. Bubbles would literally bridge across, and you get kind of a slugging pattern in your fluidized bed, not conducive to good mixing. So we had to go back in and build a series of baffles to try to get the pilot plant to kind of simulate what we expect will happen commercially. What we decided to do was to do some additional work in the coal flow regime, and we actually built coal flow models at the Particle Science Research Institute outside Chicago. We built 3, 6, 12, 18-inch, and then finally a 3-foot diameter unit to kind of simulate what would happen in various configurations. And that, then we could cross-check the results we were observing there with the results from the computational fluid dynamics. Things we were worried about: we want to be able to predict out of this model carbon conversion. We want to be able to predict the steam conversion. We've got to know the methane yield selectivity. We've got to know the effluent gas composition. There are a variety of trace components we want to track. We want to understand what the composition and character of the char is, how much catalyst do you have to put in, and then of course a whole series of design issues around the fluidized bed. Not in reference to your local river here, but the term was coined Big Blue. I think it had more to do with our trademark of blue gas. But the model basically incorporated kinetics and hydrodynamics. It has been our key design tool, and the concept is it should be able to essentially predict the performance of any size plant. So we've challenged the modelers. All right, we run an additional experiment in the lab. You've got to predict a priori how that experiment's going to come out. You run an additional test in the pilot plant. We need to be able to predict a priori how that pilot plant result will work. And at that point, then you gain some confidence that this model might be able to predict a larger plant. And essentially all of the R&D pilot and supporting experimental work was focused on this validation exercise. I'll just give you a little feel for what this model looked like. It's a kind of classic two-phase bubbling bed. We've got the chemical kinetics built into it. The hydrodynamic parameters are essentially bubble size. We've got the particle size of the solids. We've got the mass transfer coefficient between the bubble and emulsion phases. We've got emulsion velocities, bubble velocities, stages both axially and radially. The kinetic parameters for the steam carbon gasification, hydrogasification, water gas shift, CO methanation, on down through here, including the catalyst loading. And this model tends to be fairly sophisticated. It basically pictures upflow of bubble models. The coal and catalyst are flowing down in the emulsion phase. You've got exchanges between the phases. We've got both a core and annulus zone. We've got 3 reactor zones, upper, middle, and lower, so they're trying to keep track of this thing throughout, monitoring the chemical reaction both in the solid and gas phases. We're looking for what happens to the particles in the cyclones, what happens to the particle size population, what gets entrained, and then what happens as you change the diameter of the device. I think 9 different species are being tracked, some 425 differential equations, a few thousand lines of code. So it's a fairly sophisticated reactor model. Then the question comes back to management. Okay, how much do we trust the model? How big do we build the next step? And that's really the question that we've been grappling with since the end of last year. And I thought I might share that. How do we sort of balance the risk of spending a fair amount of money without being absolutely sure that the model will predict what's going to happen? The scale-up strategy within Great Point was really to focus on mitigating the risks around the technology. We wanted to make sure that we understood the catalytic hydromethanation as best we could. We also had to worry about the catalyst recovery and recycle, and that's what all the test programs in the lab and the pilot plant were designed to do. We went back to third-party studies. Exxon actually discovered the first hydromethanation catalyst back in the mid-70s, and they published a fair amount of work up until 1982 with DOE sponsorship. We've been through every one of those reports and actually been able to correlate most of their data with our model. We hired 2 engineering companies that have scaled up more fluidized beds than any other company. Lummus and Badger had them do independent risk assessments. What could go wrong scaling up this fluidized bed reactor? And then we had a survey outside that kind of proprietary technology area. Is there anything we're doing in this plant that involves any unusual risks? And so we actually looked at all the processes and equipment, looking for confirmation that they were either operating or could easily be designed to operate at the conditions we were running them. A few scale-up issues came into play. On the technical side, we very quickly figured out that the fluidized bed was the critical unit. I mean, that's our reactor. We've confirmed the chemistry at the pilot plant. The trouble is that, remember I said this is a thermally neutral reaction, but it's operating at 1300 degrees Fahrenheit. So even if it's thermally neutral, it's going to lose heat through the walls. And when you're running in a small, either laboratory or pilot scale thing, the ratio of the surface area to the volume of the reactor is simply too high to keep the heat, to keep the reaction at temperature. So even at the pilot plant, we had to install heaters just to maintain the reactor at temperature. Adiabatic operation, where the heat losses were essentially constrained, and to get to a point where the hydrodynamics, where the bubbles did not bridge across the diameter of the reactor, calculations said we'd have to be at least 3-foot diameter. Now we confirmed that for the hydrodynamics, and I think we trusted our heat transfer calculations, so we were fairly sure that we had to have at least 3 foot. As I said, we ran a unit at 12 to 18 inches. Now we've got to get to at least 3 foot to get to that next step. The catalyst recovery and recycle were considered essential, but we've got enough demonstration of them. The scale-up wasn't as critical. And no one was concerned with the balance of plant. It just wasn't viewed as critical. But at this point, the finance side gets involved in the effort. And what they observe is that, well, you build a 3-foot, we're not going to make any money off a 3-foot. It's still non-commercial. You can't get a return on an investment in a 3-foot reactor. And if you build a 3-foot, we're still going to have to build a full-size single reactor before the banks would loan us conventional project financing. So we've got an extra step in there if we build this 3-foot. We then asked the question, well, how small could we, what could we build in between? The commercial unit we estimated was going to be about 22 foot in diameter. It was about as large as we could build and fabricate in shops today and transport to site. So we backed it up and said, well, we could probably go to half scale, maybe 15 foot. We would be commercial barely, but that would be essentially we could demonstrate commercial viability at 15 foot. And the finance guys went to the banks and said, well, if you did a 15 foot, we'd have no comfort in giving you, we'd have great comfort in giving you financing for, if you wanted to build subsequent 22 foot units after that. If you were successful at 15, we'd be very comfortable with that. So those were sort of the background issues. And so we built up a couple of different paths to consider. The place we started was pilot plant. We had done that test at 1.5 foot, 18-inch diameter. Kind of the classic way of going forward was to build a non-commercial 3-foot, sort of a miniature plant with full gas recycle. Then you'd build that a single 22-foot one, and then you could build out a full commercial complex. We found a site with one of our partners where we could kind of get away with a modified 3-foot unit. We could build our reactor, our catalyst recycle, but we didn't have to build the full gas handling facilities. They had a fair amount of equipment already on site. So we lowered the cost, but we didn't test everything. So the question was, what was the delta risk? And then you completed the path. And then at the behest of some of our owners, we looked at the possibility of skipping this non-commercial step, going straight to a small 15-foot commercial plant, and then you could build out from there. Again, everybody, I think, understood that risk increased as we moved across those paths. And the question was, well, how do you decide? And so we went to what we call a formal facilitated risk assessment. We engaged 30, I think we had 32 different experts in different aspects of the plant from our investors. So Suncor sent down a delegation from their engineering department. Dow sent some of their engineers. AES sent theirs. We went outside to Jacobs Engineering, Shaw Badger, Fluor, got some of their specialists in a number of areas, and of course we had our own technical team. And then what we did was we hired a small group from Jacobs Engineering to facilitate the risk assessment. And what these experts did was go through literally every aspect of the entire facility and identify what could go wrong. And so we asked them to look at each section of the plant. What are the risks? What could go wrong as we scale this plant up? And then tell us, what's the impact? What's it going to mean? Are we going to lose yield? Are we going to lose selectivity? Are we going to lose catalyst? Is the plant going to fail? Is it going to break down? Tell us what the impact is. Tell us what the probability of these risks occurring is. And finally, is there anything we could do to mitigate the risk? Could we make an additional investment now to prevent that risk from occurring? Or is there something we could do if it does in fact occur, could we fix it? And then what Jacobs did was they collected that information. So they got this rather extensive set of expert opinions across the board, quantitative probabilities of these risks occurring, quantitative estimates of what's it going to cost you, how long are you going to be down, how far down will your yields go, how much catalyst, additional catalyst will you lose, and what it would cost to mitigate them or go back and fix them. A real key observation came out, nobody found any fatal flaws. They said, you're going to be able to fix this thing, but it could take a fair amount of time and a fair amount of money to do that. So they took all that information. Our finance people gave them the financial models for each of those three paths. And they ran a Monte Carlo simulation, just basically over and over again, number of trials. As the probabilities hit, what happens to the economics of that phenomenon, of those paths. This is kind of a typical result. This happened to be from the experts, this was just sort of the probability distribution around gasifier yield. Now on this curve, actually commercial gasifier yield would be somewhere out here. Our experts were fairly negative in the view of what the yield would be, but as you can see, after we tapped a bunch of them, we got something pretty close to a bell-shaped curve. And so that is kind of the input that's going into the model. And this is the output. It's actually a Monte Carlo simulation. This was path 3, the green. That was that most conservative path over on the right-hand side. And it came out probably the tightest distribution. In other words, we're plotting probability against net present value. You've got a fairly tight distribution. The least risky path, but also the lowest net present value. Path 2, a little less expensive step, a little faster scale up, and all of a sudden we begin to see kind of a bimodal distribution as the risks begin to impact. The spread is a bit wider, but the average NPV is improved. And the last one was, we got quite a distribution, but what we observed was that there were almost no events down here. In other words, in the worst case for this path 1, the economics for taking that path were better than the best cases for either paths 2 or 3. And after our technical committee and our board of directors asked the team to go back and run a number of sensitivity cases, the answer came back, this was the path to proceed. Yes, we run a bigger risk, and there probably will be some costs and delays and shortfalls proceeding this path, but we come out net by getting to market faster, and by saving some of the money of that additional step, we actually improve the overall economics. So that's how we actually came to the final recommendation, which was, let's go to path 1. Let's build a small commercial demonstration facility. Gives you the highest risk-adjusted net present value. When we went back to the expert opinions, what we found is that the technical risks. Forget the dollars involved, but the technical risks really were no greater for building a big one than a small one, and that the additional value you got by moving faster to market would more than cover the cost of the additional fixes that you might have there, or the more expensive fixes. The finance people got involved and said, wait a second, this is a more financeable path. It takes less equity. You only have to build the one plant on equity. We can project finance the rest, whereas paths 2 and 3 required a couple of steps, actually took a higher front-end equity involvement. The early commercialization made equity easier, and we avoided the erosion of competitive advantage. So that was what finally went forward as the recommendation, and that's kind of the path the company ended up on. The decision was to go out and raise some additional money about 2 months ago. A real bad point in timing if anybody's followed the financial markets lately. You really don't want to be raising money in this market. Our financial advisor, Credit Suisse, has pulled virtually every fundraising deal from the market except Great Point Energy. We seem to still be getting a fair amount of interest. There are a number of folks out there that have kept their powder dry, so to speak, and seem to be interested in investing in this business. So we're cautiously optimistic that we'll be able to put the financing together to move forward, but it is right now being tested. I've learned not to challenge the 3 young guys that have done this work. They've been marvelously successful at raising money up until now. They've raised something like $160 million for this company to date. They're asking for another $100 million out there to take us to the next step. They just may well pull it off. We're looking at 2 sites for that first project. There are actually 2 sites in North America. We're probably leaning toward the Tuscola, Illinois site right now. Both sites are very attractive from the standpoint there's a fair amount of industrial infrastructure around them. We'll be able to keep the cost of the first plant down to a minimum. We are well underway in terms of permitting. The communities are highly in favor of these projects in both locations, and the design and engineering is well underway. We have a competing project, however, that's risen. You only build one first commercial project. The 2 sites have been competing for the project. They say Tuscola is probably in the lead right now in the States, but this one's looking very promising. We're actually been approached by the 2nd largest Chinese power company, Datang, and they came to us and said, we've been reading about your technology. We'd like to move from simply power generation. We've gotten central Chinese government approval to get into synthetic natural gas business. They have access to large coal reserves. They obviously have kind of governmental access to natural gas markets. One of the big advantages in China is the costs of construction are much lower. We were kind of stunned at how much lower. Today, one of the things we estimated was, what does a power plant cost? A fully outfitted pulverized coal power plant facility in the United States, a brand new one. Today, I should say 2 months ago, engineering prices and construction costs are changing pretty rapidly with the market, but 2 months ago, $2,500 a kilowatt to build a brand new facility in this country. To build that same facility in China, and they tell us it's got the same environmental equipment that the U.S. facility has, $800 a kilowatt. We're talking about 1/3 the cost. Now, we're not assuming that our plant can be built for 1/3 the cost, but every indication is that you could build one much less expensively. They are very much interested in large commercial facilities in the Inner Mongolia where the coal reserves exist. They have identified a site at Foshan that's got a fair amount of industrial infrastructure that might be appropriate for the first project. It appears that we can get bank financing even for a first-of-a-kind project in China, which is totally impossible in the States. We have already engaged our own engineering firm in China, Century 3. One of the things we're interested in any event is sourcing equipment and engineering services for future plants regardless of where we build them, and China is a superb source of that. And this looks like a great way to ultimately manage the costs of projects we build back in North America. The Datong engineers just left. Well, no, I take that back. They're still here in Chicago. They're going back tomorrow, but they've been here doing a fairly intensive due diligence of the effort. And as I say, things look very, very promising. So a possibility that our first project may well be in China if the numbers work out well. The essence of the deal is that they've pretty much agreed to raise all of the money for the first project in exchange for equity in Great Point Energy. So it's looking very encouraging. And that's kind of the story of the company and the technology. Didn't get interrupted with any questions. You guys aren't quite like most of our investors. They tend to interrupt as I go through these things. But I'll be happy to answer any questions if you've got it. Sure.
I have a question. You said you were hesitant at the beginning to sort of accept the viability of this project. And
Right.
You said sort of as the investors came, you sort of came around. Was that like a gradual awakening, or did one day just happen?
Well, it was. They talk. My problem was that, as you can, the kinds of numbers that are associated with. I mean, building this first commercial project is going to require somewhere between $200 and $500 million. And here are three young guys who've been in the venture capital world where raising $20 to $30 million is a big deal. I could not see venture capitalists coming up with this level of money, and I think I'm still correct. The venture capitalists aren't going to come up with this level of money, but they were willing to stay in it for a fairly long way. I mean, we got venture capital funding of close to $40 to $50 million, and then these guys were able to leverage that into real equity financing from, the likes of Dow, Suncor, AES. So only when we got to the point where I think they looked like they could raise serious dollars to pull this thing off did I get interested. I was also a little concerned as to whether they could assemble a technical team and kind of get control of the technology. Now, I sort of cheated. I mean, they invited me to join the board back in 2004, so I've been on the board of directors of the company for that whole time. So I had a nice seat to watch what was going on. But and finally, a little over a year ago, it looked like this thing was going to go, and I said, well, I got enough energy left for one more undertaking.
What the temperature and the pressure of methanation?
What's that?
Temperature, pressure.
What's the temperature and pressure? The reactor operates at about 500 psig, 500.
500.
And the temperature is 1300 Fahrenheit, 700 degrees centigrade.
One of the scale-up problems that I've heard about is that when people scale up a fluidized bed, they sometimes make a mistake and add a little area, and it makes it operate inappropriately in terms of, it seems like it needs to be at the optimum area as opposed to...
Yeah, no, you're absolutely correct. When we look at the models, you can tell, I mean, obviously the trick with a fluidized beds work fairly well when you've got nice uniform solids, and they made cracking catalysts, the nice zeolite, smooth, manufactured things. We used to make acrylonitrile catalyst for fluidized beds. A manufactured catalyst fluidizes very nicely, nice smooth edges, nice spherical shapes. Unfortunately, petroleum coke and coal don't grind up to nice, pretty spherical shapes. You got a fairly wide particle size distribution. They've got sharp edges. They don't fluidize nicely. And as a consequence, what you end up operating is in this bubbling bed zone where the bubbles can get fairly large. We've calculated that bubbles can get between 12 and 24 inches in diameter. So those are big bubbles in this bed. And what happens is you can get dead pockets in a fluidized bed. Absolutely correct. And the dead pockets, basically, you lose your mixing, you lose the productivity of that section of the reaction. So it's been a very key thing on the small scales to get this thing to operate, and unfortunately the shape of the unit we leased at Gas Technology Institute had a couple of swages in it, so we got some definite dead zones around those swages, and we had to design baffles to sort of force the gas and put some additional gas injection ports. So we've been basically experimenting. Our ultimate design is just a simple tubular reactor, same diameter all the way up. We've been doing experiments both on the computer models and with the cold flow models of where you need to inject gas to keep the bed uniformly fluidized, what are the range of operating conditions. So we feel like in terms of the experiments we can do in cold flow, small scale hot, and computer modeling, we think we've got it about covered. And we've got a nice list from Shaw Badger of all the things that we ought to consider having designed into. So the first plant's being designed with basically little ledges where we can go back in and add baffles if we need to add them. We don't think we need them, but we can add them if we do. We've got additional ports cut into the shell. This is a 22, this one's 15-foot diameter, 500-pound vessel, so it's a fairly thick-walled vessel. So we're actually going to design it with additional gas injection ports. Don't plan on using them, but if we get some dead zones, we have the ability to put additional gas into those local areas and kind of stir up the bed a little bit. But no, you're absolutely correct. That is, the issues are always the mechanical design of the gas distribution grid, whether or not you provide any kind of baffles or channels in the reactor, and then you've always got the challenges of getting the solids in and getting the solids out of the reactor. And these are all the classic areas where you have problems scaling up fluidized beds. The old rule of thumb was, you always brought in Fred Zenz, who worked on the original CAC-Racker, and then when Fred retired, his understudy, Bob Pfeffer, was the guy you always brought in. And today there's a small cadre of people, but there's a small cadre of experts that you bring in to sort of bless all your stuff. We used to do all these calculations by hand. Now the computer gives us some pretty astonishing things. That Barracuda CFD software, they tell me, takes about 6 weeks to come to closure. So for each run, it takes us about 6 weeks to get the simulation model to closure. So these are pretty powerful tools that simply weren't available to us, 20, 30 years ago. And having said all that, I still don't trust the models. We're still making, a lot of judgment guesses here as to how to avoid problems.
Probably, tapering of fluidized bed.
Yeah, we decided that wasn't appropriate in this case. For a smooth moving fluidized solid, that seems to work very nicely. For this material, it's bad. I think I had one more question back here. Do you have a question? Yeah.
I mean, other than the catalytic cracking of the impurities in gas, what other technology GPE are you using?
Pardon?
What other technologies for the impurity cleaning out?
Oh, the gas is actually surprisingly clean. I mean, you've got, of course, got the hydrogen sulfide and the ammonia. Most gasification systems have a host of what I call cats and dogs, carbonyls, sulfides, tars, various liquors of sorts. We see almost none in our pilot work, and that was kind of surprising until we went back and looked at what the catalyst is doing. And essentially the catalyst appears because, as opposed to most of the modern gasifiers, which have, residence times in fractions of a second, our material is in the bed for almost 4 hours, and the gas has, several seconds of residence time. And apparently, as that gas and those various trace materials pass over the catalyst, they are catalytically reacted away back down to the core elements. So it's we have a series of steps at the end. Obviously we've got cooling, we've got scrubbing steps, we've put in mercury adsorption, we've got COS hydrolysis. We've got a whole series of pots and pans at the end that you would expect in most gasification facilities. And I've got kind of running bet with the engineers that we're probably not going to use any of them once we get out into commercial. But we've got them there just in case. Sure. What is the catalyst? The actual final catalyst is highly proprietary, so we don't tell people the final chemical composition, but the raw material is alkaline earth metals. So, for instance, potassium carbonate is, essentially the material. And in fact, if you go back and read the old Exxon literature, you'll notice that they did a lot of work with potassium carbonate, and that was the starting material that we've done a little tinkering with the catalyst, but you can't afford to have anything terribly expensive. So it's just a little tinkering. The real science is how to actually get that material distributed on it. But it's essentially alkaline earth metals. Sodium and calcium will also catalyze the reaction, not as well, and right now, we're looking at various mixtures of catalysts to see if we can figure out exactly what works best and get us the cheapest possible catalyst, but it's that series. Anything more exotic is too expensive because essentially it's applied to the coal, and unless you can recover it easily and recycle it, you lose it. And anything expensive simply will destroy the economics of this process.
Where is the carbon dioxide sequestration within this? Is this you might say new technology, or is it
No.
understood?
No, the technology we're using in our plant is essentially, we've got our product gas has methane and CO2. So we've got to separate the CO2 to get pure methane. The technology for separating CO2 by our design rules was we didn't want it. There's some new technologies out there. We're not taking the risk. We're going with the very conventional. The three we're looking at, and we'll pick one of the three, are Selexol, essentially an ethylene glycol material to scrub out the CO2. We're looking at Rectisol. They use methanol, or there are chemical amine systems. All of these are extensively used in the refining industry for removal of acid gases. They're used in the natural gas processing industry. Very conventional technology. So we separate the CO2. Commercially, what our plans are is each of the sites we've chosen has been selected very carefully. We have to have an off-taker of the CO2. So we are locating our plants at sites where there are already CO2 pipelines in service. And we actually have term sheets from the operators of those pipelines to buy our CO2. The CO2 is, of course, being pipelined to oil fields for enhanced oil recovery. So that's where the CO2 is going. In the future, if CO2 sequestration dwarfs the EOR requirements, and as you can imagine, at some point that could happen, then we'll worry about trying to find people who will basically put it in saline aquifers or things like that. That technology is, I think, still being proven, but assuming that it gets there. The advantage we have is we have to separate the CO2. We've already got it in pure form. Every other technology out there, that's an added cost, an added step they've got to kind of add on. So the CO2 is there, and as I say, right now we've had no trouble in identifying sites where we can sell it, and we know it will be put underground and left there for a very long time.
Yes.
I have a question about the catalysis again. Which of the steps is actually catalyzed? It wasn't quite clear. I thought it was the water gas shift.
It appears to catalyze all three reactions. Yes. It catalyzes the steam carbon gasification, catalyzes the water gas shift, and by the way, we've run the pilot plant way out of balance in syngas, and it catalyzes the methanation reaction. Now, those are equations that are those reactions are typically simplified reactions used for, because it's a complex phenomenon. What's actually occurring on the surface of the coal and carbon, there's been a host of research, and you can imagine a whole series of more complex reactions occurring, but yes, all three reactions, the net effect is a catalyzation of them. And that's the only reason it works. If it didn't catalyze one of them, we'd be dead in the water.
A
extensive economic analysis of the 3 options you had.
Mhm.
How much did that economic analysis cost?
How much did the economic analysis cost? Well, that's a good question. Jacobs Engineering probably charged us several $1,000,000 for just to run the study. And I didn't bother adding up what, we probably paid, for the experts, maybe another $1,000,000 or so, and then we contributed our engineering time. I didn't really count that all up, but I would say you're probably looking at $4 to $5 million all in. It was not a trivial effort.
So if you feed in all solid, how much of it comes out as gas? Does it all come out as gas, or is a significant through one pass?
It depends. For instance, Powder River Basin coal, you got about 10% mineral matter or ash in the coal, and for simplicity, let me say the other 90% is carbon. Not quite true, but for simplicity. We will typically run that to a 90% conversion of the carbon. So you'll have about 10% of the carbon left, and then you've got the 10% of the ash. So when you pull an average particle out of the bed, it's half carbon, half ash, plus it's got our catalyst on it. And then we basically wash that to recover our soluble catalyst and recycle that. And then that low carbon, high ash char, if you will, is actually sent to that partial oxidation unit, and we basically burn off the last of the carbon and recover the final mineral matter as a sort of a glassy slag. So now petroleum coke, the ash content's maybe about 0.5%. We'll typically run that reaction to 96, 97% carbon conversion. So you'll get a material out that's probably 70, 80% carbon with a little bit of ash in it, and then we scrub that and then send that to the partial oxidation unit. And it's really just as those curves bend over with more residence time, you sort of make an economic optimum choice of how far you want to squeeze them in the fluidized bed before you just kind of say, that's enough, let's burn the rest of it, clear it off.
Well, thank you very much.
Welcome.
So we will meet Thursday. At that time, we're going to try and develop a list of things that we should do in this world to make it sustainable. And so come to share your ideas, and guests are welcome then as well. Donald, thank you very much for being with us.
Thank you. Appreciate the invitation.